Hey, this is Dr. Doobie again. Hey, what do you do if you need vapor-liquid equilibrium data, but it's not an ideal solution? Let me show you a trick. Suppose we want to distill an acetone isopropanol mixture at 1 atmosphere. How do we get the vapor-liquid equilibrium for this system? If it's an ideal liquid, we can use Raoult's law. Raoult's law states that the partial pressure, which is the mole fraction in the vapor phase, times the total pressure, is equal to the vapor pressure times the mole fraction in the liquid phase. So we'll say X times P star for the vapor pressure. Now the vapor pressure is usually calculated using Antoine's equation, which has the form log, that's log base 10, of the vapor pressure is equal to a constant plus a second constant divided by the temperature and a third constant. You have to pay attention to the units used in this equation. The constants in the appendix of Felder and Rousseau use the temperature in degrees C and the vapor pressure in millimeters of mercury. But in the NIST data tables, the temperature is in Kelvin and the pressure is in bar. And sometimes you'll find resources that have the natural log here rather than the log base 10. So lots of things to pay attention to, but you should get the correct answer if you use the right units. Now, of course, I'll rewrite this as the vapor pressure is equal to the, as 10 to the power of A plus B over T plus C, like that. Now, if the system is not ideal, we can use a modified Raoult's law, which has a vapor phase fugacity coefficient times the mole fraction in the vapor phase times the total pressure is equal to an activity coefficient times the liquid phase mole fraction times the vapor pressure. We usually assume the vapor phase is ideal, and so the fugacity coefficient, which accounts for the non-ideality, is actually 1. But the liquid phase oftentimes is not ideal and will need an activity coefficient to calculate the vapor-liquid equilibrium. There are many models used to determine the activity coefficient, such as the Wilson equation or the NRTL or the UNIFAC equation. Which one to use usually is based on which one fits the experimental data best. Those equations can get quite complicated, so is there an alternative that we can use? Here I've plotted the mole fraction in the liquid phase versus the mole fraction in the vapor phase. The red line is using Raoult's law, and the blue line is using the NRTL equation. That's the non-random two-liquid model for the activity coefficient. This is the model that the thermodynamic wizard of the process simulator ChemCAD chose to represent the experimental data. The question I have, though, first of all, was that a really good model? Here I've added actual experimental data from the Dortmund database, and this is the original article that they're referencing. And you can see here that, well, this data is for 1 atmosphere, and it's not quite on that line created from the NRTL equation. What to make of that? I will assume that the ChemCAD program is using a broader database than just this one article, and that the NRTL equation actually gives us a better fit of most VLE data. For the purpose of this demonstration, I don't really have time to do extensive research on this. If I was actually designing an acetone isopropanol distillation process, I might want to spend a little bit more time making sure that I'm using good VLE data. But for right now, let's just go ahead and use what ChemCAD gives us. Here I've plotted the TXY data. And so this curve here is the dew point curve using Raoult's law, and this is the bubble point curve using Raoult's law. And you can see they're quite different than the dew and bubble point curves generated from ChemCAD using the NRTL equation. Again, I've added the experimental data for the bubble point, or this is the dew point and the bubble points. And, there are parts of the line where they're pretty close, especially on the dew point curve. But overall, they're not exactly right on the predicted line. But again, we'll use the NRTL equation anyway for this demonstration. On this XY diagram, I have left off the line using Raoult's law, and now I just have the line from the NRTL equation. And I have fit it with a polynomial. And here's the polynomial. It's a 6th order. That gave me an r-squared value of 1. And you can see from this that you can't really see the polynomial equation because it's right on top of the data. And so this polynomial equation says basically that y is equal to this function of the x value. So if I know the x, or the liquid phase composition, I can find the vapor phase composition that is in equilibrium with that at 1 atmosphere using this polynomial equation. And I'll use that in any kind of simulation of a distillation column. It turns out that what would be more useful for me in the way I set up the simulations, as you'll see in a future tutorial, that it would be better if I could find the x value, the mole fraction in the liquid phase, knowing the mole fraction in the vapor phase. And so I just turn that graph around. And then again, I fit it with a polynomial equation. A 6th order polynomial gave me an r-squared value of almost 1. And in this case, y is actually x, and x is actually y. Just keep that in mind. It can get a little confusing. We can also replace the TXY data with an equation by fitting it. And in this case, I fit the dew point equation up here, and we get actually a really good fit with just a 4th order polynomial, which makes things a little simpler. An r-squared value of 4 nines. And in this case, the y is t, and the x is actually the mole fraction in the vapor phase. That's why this axis here is both liquid and vapor phase mole fractions. So the dew point curve is for the vapor phase. The liquid phase is represented here by the bubble point curve, and that's also fit pretty well to a 4th order polynomial, which is shown here. Finally, for this demonstration, I have summarized the polynomial equations that will be used to simulate distillation. And in this case, I've got the equation for the dew point, the bubble point, and that yx curve. And in this, over here, I show what is actually calculated with this polynomial equation. In this one, the temperature is a function of the vapor phase mole fraction. That's the dew point curve. And so it's the vapor phase concentration to the 4th power, actually mole fraction to the 4th power, and multiplied by this constant, plus that to the 3rd power, multiplied by this constant, etc. The bubble point curve gives you the temperature as a function of the mole fraction in the liquid phase, and the y-x curve gives us the mole fraction in the liquid phase, knowing the mole fraction in the vapor phase. That's all I want to say about polynomial fitting. We'll actually use these polynomial equations for the design of a distillation column using this non-ideal system.